Hello, everyone. Um, for those who have joined, um, I'm doing another NAPLEX overview with you all to go over some concepts. Some of you might have some questions on these types of topics, so just a refresher, we're going to go over some pharmacy calculations as part of the NAPLEX overview. Um, these are some of the kinds of topics that they may ask on the exam. So I thought I'd like to post a little refresher here. So hopefully it kind of helps you all in understanding some pharmacy calculation concepts. Um, Obviously, the very first thing on this bullet point is understanding the unit conversions, like converting to different types of units, liters to milliliters, those basic ones, and then converting also to ounces. Having that kind of basic concept understanding is very important, especially in practice. For those who are in hospital or have had some experience as an intern, or even if you've had, even while as a pharmacist, might be shadowing some other pharmacists over there. Um, you may have seen how important calculations is, especially when you're giving IV injection to patients. So this is a very important thing um, to understand, to know, having those kind of unit conversions, especially for patients who are on insulin and all those kinds of situations. It is very important. And that also includes understanding how to calculate TPN, or total parenteral nutrition, um, you know, information that where the conversions occur when you have to convert proteins and dextrose and other types of nutrients that's needed in when administering any type of IV fluid medication to a patient. So we'll take a look at a little bit of that TPN concepts and some examples there. Also some isotonic concepts and calculations, dilutions, osmolarity on osmolality, um, some information on IV flow rate. So a lot of this looks like an acid, as you would see in a hospital practice or in a clinical practice. So it's very important to actually have an idea how to perform those types of calculations, so that um, you can get the correct, give the correct amount to a patient, and also understanding how to calculate for the exam as well. So let's take a look. Um, so here I have some charts here you guys can use, just to look over. But when it comes to the exam, I believe you're going to have to know all of these uh, types of conversions, or most of these conversions. As you can see here, like grams, milligrams, micrograms, grain, ounce, pound, kilogram, all of those basic ones. They're probably not going to have, uh, they may or may not have it on exam, but it is a good idea to have an understanding of that. You could see on the right side, there's two different types of conversions here. You could see the top right, um, all of these are liquid conversions. Um, there may be some variation, so definitely refer to your book when you look at some of these conversion values. They might not be exactly the same as the one I have listed here. Um, so Um, but it is very, very important to have an idea as to what these conversions are, how to use them in calculations and also in practice. Um, and then you can see here on the bottom right some of the other types of conversions that is also important, especially when you're doing percent weight or volume, percent volume or volume, and percent weight or weight. The ratio strength, the parts per milliliter, and then the are you know, then parts per liter, and ppb and ppms. So know all of that. And then, so let's look at the first example here in IV flow rates. You can see here the two different formulas here. Milliliters per hour equals to total volume per which is in milliliter, divided by time hour. So you could see when it comes to giving an IV fluid to a patient, obviously there has to be some kind of time involved in it, so that this is how much milliliters you're giving per hour. So that's essentially what's happening here. Or if there's a drop, you could see here the drop factor times the milliliters divided by the minutes. So an example here is a patient has ordered 1,000 milliliters of 0.9% sodium chloride to infuse over 8 hours, which will be a flow rate in milliliters per hour, be if using an infusion pump. So automatically you could think it's 10 milliliters per hour. So it's not going to be using any, it has nothing to do with the drops. So I'm going to use that first formula here. So in this case, what you should do is you definitely want to just divide the two numbers and you get the 125 milliliters per hour will be your flow rate in this case. The next one here involves the flow rate formulas. This one uses a drop factor of 15 drops per milliliter. And you need to infuse 500 milliliters over 4 hours using IV tubing with a drop factor of 15 drops per milliliter. And what is the flow rate in drops per minute? So now you have hours, but you have to convert them to minutes. So you definitely want to multiply that by 60 because they're 60 minutes per hour. So you can get the minutes there. And then you could multiply the 15 drops by the 500 milliliters just to cancel over that milliliter unit there. And you would just divide by the number of minutes you calculate. That would get you your drops per minute. So this is the answer here, the solution, so you can see how that works. The next one here involves osmolarity and osmolality. Osmolarity is the solid particles per liter of solution. So solid particles, okay, per the liter of the solution, and they are represented by MOSMOL, milliosmoles per liter. So you could see the formula there, and basically you would just take the grams per liter, divide by the molecular weight, multiply it by the number of particles of compound it dissociates into, and then times it by 1,000. That's how you would get that osmolarity. So in this case, example is involved to calculate the osmolarity of 5% dextrose solution. So you would just have to figure out what the molecular weight of dextrose is. They might be given on the exam, but at least have an idea as to what it could be. And in the grams per liter, you can calculate that out as well. And so because 5% is equivalent to 5 grams per 100 milliliters, it would just be 50 grams per liter. You could just move the milliliter, 100 milliliters divided by 1,000 to move it over the 3 decimal places to the left, and then you divide them to get the 50 grams per liter. And then you will then divide that by the 180 grams, which is the molecular weight, grams per mil. And then, once you get that answer, you multiply by 1, because just one particle, dextrose, cannot be dissociated. So it's just going to be one whole particle, and you would multiply by 1,000. And that's how you get 278 milliosmoles per liter. So, and this is some extra information for your reference. So that's pretty much it there. Next one is osmolality. It's kind of similar to osmolarity, but it divides by kilogram instead of a liter. And it uses a slightly different formula here. You would use the 2 times the sodium plus the glucose over 18 plus BUN over 2.8. And that's what you would do in this case. You would just plug in the values as per shown on the example here, where the patient has lab values showing this. Sodium equals to 144 milliequivalent per liter. Then you have glucose, which is equivalent to 180, and then BUN, which is equal to 28, and then you would just calculate the plasma osmolality. So it's a good idea to have an understanding of this formula as well for the exam, so at least you can calculate the plasma osmolality when you're looking at a patient case and you see the different values associated in their labs. And so that's how you would calculate there. Then you got basic dilution problems. In dilution, you're just basically multiplying the C1 times V1 equals C2 times V2. That's this concentration, this stock volume used. And then it would just equal to a final concentrate, final volume. So there is a question here. You have 10 milliliters of 10% solution. How much water should you add to make a 2% solution? So basically, again, it's like a C1 V1 concept. But in this case, it's asking you add 2. Don't forget that keyword, add 2, because that's very important. You want to just figure out what the volume is. You also have to figure out how much water to add to it to make the 2% solution. So you basically multiply the 10 milliliters by 100, and you get by 10 milliliters by times the 10% solution, you get 100 basically, and then you would divide by the 2. You might get the 50 milliliters, but you also have to remember that that's just a solution, but how much water should you add? So you have to definitely do a little bit extra math there. So you just subtract it by the 10 milliliters that you originally started with, and you would get the 40 milliliters of water that you should add to make the 2% solution. So very simple concepts. Just make sure you pay attention to some keywords in the questions when you answer these, because things like add to, I think this one, plasma osmolality, looking for these types of things, and understanding the units here between osmolarity and osmolality is important. Isotonicity is a different topic here. This one involves the 3 types of isotonicity concepts: hypertonic, hypotonic, and isotonic. They may be confusing to some people, so here's some ways to remember it. Water generally moves where there is more solute. So when you look at plasma cell, concentration is divided up into solute and solvent. Solvent follows where there's more solute. So when think of water as a solvent and sodium chloride as a solute. So water is changing the way a cell becomes, whether it moves inside or outside of cell. If there's sodium inside the cell, then water. The water is going to move inside to make it more hypotonic or swollen. And the same way, as more sodium chloride being outside, then it will cause the cell to shrink, causing it to be hypertonic, or to give it becoming more excitable, or letting it out from inside, kind of letting it out. So hypertonic. And then like a hyperblast, like taking it out. And then if both concentration inside and outside is the same, then it's isotonic and there's no net movement. So it's kind of like easy little tidbits to ways to remember the different types of tonicity types here. Also understanding the common isotonic reference is important, and this might be a little bit small to some of you, so I'm going to kind of enlarge it here a little bit. But you can see here, like sodium chloride, dextrose, plasma osmolality, like these are just some reference values you might find important to use. Sodium chloride equivalent E value formula. This is typically how you would calculate 17 times the I divided by molecular weight. And then the sodium chloride needed, which equals to 0.009 times the volume minus E times the amount of drug. So I guess there's a question here. Prepare 30 milliliters of a 1% solution of drug X. E value of drug X equal 0.18. How much sodium chloride is needed? How much sodium chloride to add to make the solution isotonic? So you would just go ahead and calculate the amount of drug in the solution. So that 1%, which is equal to 0.001, and you would just multiply that by the 30 milliliters and get the 0.3 grams. And then you will use the formula, which is right there, sodium chloride needed. And then you would multiply that by 30 and then subtract the 0.18 times the 0.3, because the E value of drug X is 0.18. So you would just take that and plug in the formula. And you would get 0.216 grams of sodium chloride that you would add to make the solution isotonic. So essentially, that's what you would do in this case. So you may or may not see a lot of this type of question on the test, but it's good to know how to do these types of calculations in case you were asked a question about it. So just take a minute to look through that. And then TPN concepts, as I mentioned, like dextrose, amino acids, lipids, these are some very common types of reference values that's used when doing or performing any type of TPN calculation. So make sure you understand that. Also, the lipid emulsion values are also important, and the dextro kilocals and the protein kilocal and the lipid kilocal. So like understand those types of formulas as well. And if this is a question here, you guys can use as a reference. A 60 kilogram patient requires TPN. The physician has ordered calories, which is equal to 30 kilocal per kilogram per day. Protein, 1.5 kilograms per kilogram per day. Lipid calories, 30% of total kilocalories. And then TPN ingredients available. You can see here dextrose 70%, aminosin 10%, and intralipid 20%. Calculate how much of each macronutrient is needed. So what you would do here is, first step, you want to find out the daily calorie requirement. Okay, how much total is daily needed? And then you would just kind of split the problem up into different parts, calculate the protein amount, the lipids amount, the dextrose amount, the protein amount. You would do it this way, and then you would also get a lipid, and then you would calculate the dextrose amount here. And so these are the little different steps that you would just have to follow to calculate it. So you'd have to do it pretty quickly because, this is a timed exam. So if there's a question on this, this is a question you want to really finish thoroughly, fast, and correctly. So just do your best to try to be able to answer these types of questions, correctly. And then the last one, I think this is one of the other ones that I wanted to go over, was alligation method. There's two types, alligation medial and the alligation alternate. Alligation alternate looks like this kind of cross here. You can see here the high percent, the low percent, the target percent, the low parts, high parts. So when you're mixing like two different types of creams or two different types of strains of like a cream or something like that, you would actually just plug it in this alligation alternate method, and you can use it to find out how much is needed to make that amount of that cream or ointment. So just an example here, to mix 10% and 2% hydrocortisone to make 5%. How much of each is needed to make 100 grams of 5% ointment? So you would just figure out the X and Y values here. And alligation medial is a little bit different. You would just kind of, if a pharmacist mixes 100 milliliters of 10% solution, 200 milliliters 5% solution, what is the final concentration of 300 milliliters of mixture? So you would just kind of figure out the amounts of each one, and then you would divide it, and then you would get your concentration. So just take a look at these problems and see how to solve them. And then electrolyte calculations are also important, especially milliequivalent and milligrams. When you're trying to convert between milligrams to milliequivalents and vice versa, it's important to know that. These are some tables and equations, formulas, and then some of the electrolyte and values shown in this table here too. So you can use it to practice some of the problems here. So you could see here how many grams of potassium chloride are needed in 30 milliequivalents. You'd first need to get the total weight, obviously, and multiply by the milliequivalents, and then get that amount there. some molecular weight, and then you would multiply it, divide by valence. And then the next question here is, a 60-year-old patient admitted with hypokalemia. The physician orders for add 40 milliequivalents of potassium chloride to 1 liter of normal saline. You're using a potassium chloride vial labeled 2 milliequivalents per milliliters. How many milliliters of potassium chloride do you need to add to the IV bag? Well, you would just simply just take the 40 milliequivalents and multiply by the 1 milliliter, divide by the 2 milliequivalents, and then you will just get the 20 milliliters of the potassium chloride that you would need to add to the IV bag. And then for renal function dosing, these are some of the equations here you could use as reference. Notice certain things here. The adjusted body weight is used only if there is 120% over the ideal body weight. So if the actual is over 130% more than ideal body weight, then you would use it. Or BMI is over 25, it would consider overweight. So just note some of those kind of little things here. A 65-year-old female patient is height of 5 feet 4 inches, weight 85 kilograms, serum creatinine 1.2 milligram per deciliter. So we would just estimate her creatinine clearance using the Cockcroft-Gault equation. So note that, and note that it's a female, so you would have to multiply the 0.85 if you're going to use the CRCL formula. So don't forget about that, what weight should be used. So in this case, you would just do that. At actual over ideal body weight multiplied by 100, you would just use that formula here. So first you will get the ideal body weight using the equation, and then you get 54.7 kilograms. The actual body weight was 85, so you go ahead and divide it by 54.7 kilogram and then multiply by 100. And notice it says 155%, so that means it's definitely overweight. And then you would just go ahead and find the adjusted body weight by taking the equation 54.7 plus the 0.4 times 85 minus 54.7, which equals 66.8 kilograms. Multiply that in the equation with the Cockcroft-Gault formula of 140 minus 65, then multiply that by 0.85 divided by 72 times 1.2. And you would get the 49.3 milliliters per minute, and that would be essentially your answer to that problem. And so yes, adjusted body weight would be used in this case, in this example. And then the aliquot, I'm going to try and make it a little easy for you. It's essentially just taking a look. If you look at this diagram, you can see that we are trying to measure 5 milligrams of drug, but it's too small to weigh accurately because the scale can only weigh minimum of 120 milligrams. To make it weighable, we dilute it and find out how much of that drug we need to mix. Drug plus dilute to make it equivalent to 5 milligrams CD. So I would spend 5 minutes just taking a look at this example slide here, because some of you guys might get a little confused on this. So just take a look. You could see how there's a 5 milligram drug, right? It's mixed with the diluent, and then there's a 5% error, but we can we're trying to get that 5 milligrams of that drug out of the quantity that needs to be weighed. So you need to prepare a capsule containing 1 milligram drug A. The minimum weight or bulk quantity for your balance is 120 milligrams. How can you accurately measure and prepare this using our quant method? So I created my example here. You can do any number you'd like. I picked out 1,000 milligrams of total mix and 100 milligrams of the drug A. So you get 900 milligrams of lactose. And then you would take that divided by the 1,000, and then you get 0.10 or 10% concentration. And then you would just take the 4 milligrams and then divide by the 0.1, and you would get the 40 milligrams of the mix. And the last one here is a reconstitution. It basically there isn't really any formula much to this, rather than just understanding concept of how to convert things from one to another. So a bottle of Augmentin is 250 milligram per milliliter per 5 milliliter of oral suspension contains 3.57 grams of amoxicillin clavulanate powder. So the label says to add sufficient water to make 70 milliliters of final suspension. So how would you do that? So first, what is the concentration after the reconstitution? So you need to figure that out first. So essentially, you would just go ahead and multiply that out and divide by the, multiply that 3,570 divided by the 70 milliliters, and you get a 51.51 milligram per milliliter concentration. Okay, and then you would subtract that by the 20 milliliters. Okay, now that's in step 2, because asking how much water should you add if the powder takes up 20 milliliters of space. So that's essentially what you do here. And the third part, how many milliliters will you dispense for 250 milligram dose? So you're going to need to take that 250 milligram, multiply by that concentration with about 1 milliliter over 51 grams, and you get 4.9 milliliters. So you just have to read the problem and see what they're asking for. And the first question is concentration. It's kind of like a percent kind of problem, milligrams per milliliter. Second one, they're just asking how much water you should add. So you have to do some kind of subtraction here, because the powder takes up 20 milliliters of space. You would just subtract the 70 milliliters of concentration by 20 milliliters, so you get 50 milliliters of water. Then the third step is really just another one where you have to figure out how much milliliters of the concentration you need for 250 milligram dose of the concentration. So you just go ahead and do the conversion there, and you would get the answer. And then pharmacokinetics, there's a whole lot of different topics here on pharmacokinetics. A lot more dealing with the infusions, the IV bolus concentration, the single dose concentration, and then the average concentration of multiple dose regimen, time to max concentration, clearance, continuous infusion, Chale equation. I have just listed a few of these topics. There's a lot more into it, but I don't think the exam's going to go too much in depth on it, but there is a possibility that you could see some questions on any of these. So just for your reference, I did post a slide here with all the equations here that you could possibly see on the exam. So just know these equations. You can go ahead and work through and try to figure out what the equation is on each of these. This is just a little quiz here you can take just to quiz yourself on what the equations are. Um, and then some example questions here you can go through and practice as well. Like elimination rate constant, half-life, initial plasma concentration. I will post some more questions on these kinds of questions, but definitely on these kind of topics. But definitely take a look in your book to see, what they could ask on pharmacokinetics as well. So that's pretty much it. I hope you all had a good little refresher on certain pharmacy calculation topics, and has been helpful to you all. And if you have any other questions, please feel free to let me know. You can comment on any of these videos, or you can leave a question, or you can send a message on Facebook, or feel free to use the resources that's available. So there will be more videos coming soon. So just stay tuned for more updates. And if you have any questions, please let me know. Thank you for watching. Have a great night.